I'm Kevin, and this video is basically a status update on my research, which can be explained in a previous video here and is also linked in the description below. I recommend you watch it just so you can understand everything that I'm going to be talking about in this video clearly. Alright, so, since my last video, not only have I been able to alter my solar absorber so that it works without the need for batteries, but I also got the opportunity to intern at Alliance Technologies, where I both learned a lot and was also able to test my hydrogel using this differential scanning calorimeter and this scanning electron microscope. The DSC testing was done on a hydrated hydrogel. This means I basically added water into the hydrogel I previously freeze-dried in order to test the amount of energy required to evaporate the water back out of it. The settings used for the DSC was a heating rate of 5 degrees Celsius per minute until it reached 100 degrees Celsius, and I also used a constant flow of inert gas, in this case nitrogen, at 50 milliliters per minute. The curve generated from the DSC is shown here, and as you can see, after a while, the heat flow and the weight percent lines begin to plateau after 20 minutes. This is due to the water being mostly evaporated out of the hydrogel. However, the water only returns to its original dehydrated weight after 100 minutes. But the majority of the weight is lost within the first 20 minutes, making it no surprise that after analyzing the data generated by the DSC, the lowest evaporation enthalpy is reported around 17 minutes. Now, as you can see, there is an equation here at the top, which is what I'm using to calculate the evaporation enthalpy. So let me take you through it. The energy that the DSC puts into the hydrogel is called heat flow, which is measured in milliwatts, but we want joules per gram. So the way we get that is by multiplying the average heat flow, which is in millijoules per second, by the time that the machine has been running, which gets us to millijoules. We can then put the millijoules over the change in mass, which is in milligrams, which gets us to joules per gram. 1851.54 joules per gram recorded at 17 minutes is actually pretty efficient. For reference, the known vaporization enthalpy of water is 2,260 joules per gram at 100 degrees Celsius. But in order to get water to 100 degrees Celsius, we need to take the specific heat multiplied by the temperature change from room temperature, and then add that to the vaporization enthalpy, which gives us a total of 2,600 joules per gram. Now let's also look at the images generated from the scanning electron microscope. The images collected by the SEM, compared to that of the simple microscope, allows for a closer comparison. The pore sizes are clearly larger in the negative 80 degrees Celsius freeze-dried hydrogel, but more interestingly, so are the cross-links. This, I believe, can be attributed to the fact that the hydrogel freeze-dried at negative 196 degrees Celsius, shown on the right, was freeze-dried a total of 10 times, whereas my hydrogel, shown on the left, was only freeze-dried once. This means that my hydrogel's crosslinks likely still have water bonded to them, resulting in the thicker crosslinks you can see. This, as well as the pore size, may also be what resulted in different evaporation enthalpies, as the hydrogel shown on the right has an evaporation enthalpy of 1,499 joules per gram, and mine has an evaporation enthalpy of 1,851.46 joules per gram. In conclusion, there's a lot more research to be done. Research that I look forward to conducting during my next 4 years at Carnegie Mellon, and hopefully using to help those in need. Thank you again for watching.